In this video, I'm going to find the series solution for differential equation y double prime plus y is equal to 0. Let's go ahead and start with the series. Our series is going to be y is equal to summation n is equal to 0 to infinity a sub n x to the power n. We are making the assumption that this series is going to be the solution to this differential equation y double prime plus y is equal to 0. Now this could be expanded to a0 plus a1 x plus a2 x square plus a3 x cube plus dot dot dot. That gives me y value. Now what is y prime? Is easy, just take the derivative term by term. So it's going to be a1 plus 2a2x plus 3a sub 3 x square plus 4a sub 4 x cube plus 5a sub 5 x to the power 4 plus dot dot dot. Then I could do double prime. That's going to be equal to 2 times 1 a sub 2 plus 3 times 2 times a sub 3x plus 4 times 3 times a sub 4 x square plus 5 times 4 times a sub 5 x cube plus dot dot dot. Okay, now this I could sort of like generalize. Y double prime is equal to summation n is equal to 2 to infinity n times n minus 1 a sub n x to the power n minus 2. So how does this work? Let me tell you. So if n is equal to 0, 2, you're going to get 2 times 1 times a sub 2 times x to the power 0, which is 1. If n is equal to 1, you're going to get 3 times 2 times a sub 3 times x to the power 3 minus 1, which is just x. And you'll get each of these terms for this. Now what we are going to do is we are going to kind of shift the indices a little bit. I'm going to replace n by n plus 2. The effect of this is going to be like, instead of starting n from 2, we're going to start n from 0. That's basically why I'm doing it, so that we have consistency. So y double prime is equal to summation n is equal to 0 to infinity. Okay, now each n is being replaced by n plus 2, remember. So it's going to be n plus 2 times n minus 1 a sub n, but now it's going to be a sub n plus 2 times x to the power n minus 2. But n is being replaced by n plus 2, then n plus 2 minus 2 is just n. And you can check it by plugging in n equal to 0. You're going to get exactly this series. Now that's my y double prime. So my equation says y double prime plus y is equal to 0, right? So I could just plug in the y double prime and y into this equation. That's going to give me summation n is equal to 0 to infinity. Okay, n plus 2 times n minus 1 a sub n plus 2 x to the power n. That's just the first term. Then the second term, again summation n is equal to 0 to infinity a sub n x to the power n. This is nothing but the original assumption, and all of that equal to 0. So now you have indices kind of aligned, all starts from 0. So I could rewrite it as summation n is equal to 0 to infinity, then n plus 2 times n plus 1 times a sub n plus 2, then plus a sub n, all of it multiplied by x to the power n, and that is going to be equal to 0. All right. So if you look at this equation, the left-hand side is actually just a polynomial, right? Kind of infinite dimension, I guess. Okay. So on the right-hand side is 0, right? Now the coefficients on both sides must be equal. So that means basically this guy is always going to be 0 because on the right-hand side we have 0. So that tells me the following. A sub n plus 2 times n plus 1 times a sub n plus 2 plus a sub n is equal to 0. If I solve for a sub n plus 2, I get a sub n plus 2 is equal to negative a sub n over n plus 2 times n plus 1. And this, by the way, is called the recurrence relation. That means it kind of keeps repeating. Now, remember my n, okay, don't forget that my n goes from 0 to infinity. So this relation, recurrence relation, is true for n is equal to 0, 1, 2, 3, etc. Now I could just plug in the values. So find out some values for n, a sub n, and see what we get. So when my n is equal to 0, so let's go ahead. When n is equal to 0, I'm going to get a sub 2, right? Because 0 plus 2 is 2, is going to be negative a0 over n is 0, so it's going to be 2 times 1, 2 times 1, or negative a0 over, I could say, 2 factorial. So now for n is equal to 1, what am I going to get? A sub 3, right? So a sub 3 is equal to negative a sub 1 divided by n is 1. Remember, 1 plus 2 is 3. 1 plus 1 is 2. So 3 times 2, which I'm going to put negative a1 over 3 factorial. Now I can continue this journey, and I'm going to get the following values. For n is equal to 2, I get a sub 4, and this turns out to be a0 over 4 factorial. Then for n is equal to 3, I get a sub 5, and it turns out to be a1 over 5 factorial, and a6, a7, etc. If you look at this pattern and you notice that a sub 2n is negative 1 to the power n divided by 2n factorial times a sub 0, and a sub 2n plus 1 is negative 1 to the power n over 2n plus 1 factorial times a sub 1. Now I can put it all together. So y, remember my y was this. Y is equal to summation n is equal to 0 to infinity a sub n x to the power n, right? Now I can break it into two pieces. Summation n is equal to 0 to infinity, okay, a sub 2n times x to the power 2n plus summation n is equal to 0 to infinity a sub 2n plus 1 times x to the power 2n plus 1. What I have done here essentially have taken the even terms together and taken the odd terms together. Why have I done that? So that I can plug in this value and this value. If I do that, I get the following. So my y is this term here. So y is equal to, look at this a sub 0 in front, summation n is equal to 0 to infinity, this term, times x to the power 2n, and a plus a sub 1, again summation n is equal to 0 to infinity, this term. Now, if you look at it closely, you notice that y is equal to a naught times this, right? This is nothing but the Maclaurin series for cosine of x. So this is going to be cosine of x plus a1, which is this, times this guy. That's nothing but Maclaurin series for sine of x. So your solution to the differential equation is this. However, we wanted a series solution for this differential equation, right? So this is probably what we want. But I just wanted to go ahead and take the next step and show you that this is actually what it turns out to be. I hope that this discussion was helpful. Thank you very much.